Thank you for joining us on Synthesis Workshop. In today's installment of our Advanced Organic Chemistry course, we're joined by Dr. Thomas Verheyen. Thomas has actually joined us once before in a Research Spotlight episode, and we're very glad he's come back to join us as a lecturer in this course. Thomas earned his bachelor's, master's, and PhD from KU Leuven in Belgium. The focus of his doctoral work was supramolecular catalysis and the development of new methods in transition metal catalysis, supported through high-throughput experimentation techniques. During that time, he did some work at Janssen and Beerse, and he also carried out a research fellowship at the University of Ottawa, working in the group of Professor Stephen Newman. Thomas subsequently became a postdoc in the Respiri Consortium at the University of Antwerp in Belgium, and he currently works as a scientist at Janssen in process R&D. Today, as we continue our transition metal catalysis module, Thomas will give us an overview of traditional cross-couplings. And from there, I'll hand it over to you, Thomas. Thank you for joining us to speak on this topic.
Thank you, Matt, for the introduction and the opportunity to again contribute to this wonderful platform. Hello to everyone listening, and welcome to today's episode of the Transition Metal Catalysis series in the Synthesis Workshop Advanced Organic Chemistry course. First, we will have a look at transition metal catalyzed cross-couplings in general. Secondly, we will have a brief look at the origin of cross-coupling reactions. Next, we will look at the most popular cross-couplings and their related key publications. And finally, we will cover some key developments in the field of the past 30 years. Metals have an important role in organic chemistry, especially in the field of cross-coupling. In essence, all cross-couplings discussed today, with the exception of the Heg reaction, can be simplified as a coupling of an electrophilic organohalide with a nucleophilic partner. Depending on the nucleophilic partners involved, different reactions have been developed over a 30-year span. In general, all the reactions in the list below follow the same simplified three-step mechanism, which is first oxidative addition, followed by transmetallation, and finally reductive elimination to generate the final cross-coupling product. The individual steps are discussed in more detail in another episode. Also, the Heg and related reactions will be discussed in a separate episode. So where did transition metal catalyzed cross-couplings come from? Critical to the development of cross-couplings are the stoichiometric metal-promoted homocouplings reported more than 150 years ago. For example, copper-mediated processes were developed early on in the groups of Glaser and Ullmann. While both rely on stoichiometric copper, the Ullmann methodology is different since a carbon-halogen bond rather than an unfunctionalized carbon system was used in the dimerization. The synthetic potential of the copper-catalyzed homodimerization developed by Glaser was, for example, demonstrated in the industrial synthesis of indigo by Bayer. Even earlier, the ferocious reactivity of sodium and potassium alkali metal reagents was exploited in the homodimerization by the groups of Wurtz and Fitt. Of course, the high reactivity of both reagents strongly limited its applicability. The first to use Grignard reagents in a coupling reaction was Turner, who reported the dimerization of these reagents mediated by initially chromium and a few years later by copper. Moving away from the harsh reactivity of alkali metal reagents to Grignard reagents is a significant improvement, but all the processes shown here rely on harsh conditions, stoichio or superstoichiometric metal reagents, and the transformations are limited to homocouplings. The first use of catalytic rather than stoichiometric amounts of metal can be traced back to the work of Job, Meerwijn and Keresch. Job, far ahead of his time, reported in 1924 that phenyl magnesium bromide in the presence of nickel chloride generated a derivative able to react with various gases such as ethylene, carbon monoxide, and hydrogen. In the example shown, published 1 year later, he successfully isolated hydrocinamic acid and demonstrated that the reaction outcome with a fixed amount of ethylene was independent of the amount of nickel used. The work by Meerwijn in 1939 on copper-catalyzed coupling of aryldiazonium salts with alkenes leading to coumarins and cinnamic acids is also an early example of catalytic metal use. However, neither of the two contributions was picked up by the scientific community. In contrast, the work of Keresch was picked up by the scientific community, maybe because he provided a systematic and more detailed investigation of carbon-carbon couplings in a series of publications, starting with the first publication in 1941. The key breakthrough report was published 2 years later, in which he described the cobalt-catalyzed cross-coupling of phenyl bromide with aryl magnesium bromide. This represents the earliest detailed report of a cross-coupling rather than a homocoupling, and thus Keresh can be considered as the grandfather of carbon-carbon couplings. Starting from this point, multiple groups got involved, and especially the subsequent work of Kochi and co-workers on the mechanism should be highlighted, since it helped to further understand and develop the field of cross-couplings. Several years later, also the first catalytic copper carbon-carbon bond formation reactions were reported by Dtsch and Castro-Stevens. These examples represent a breakthrough because they provide a desired product with high selectivity, avoiding the undesired competing homocoupling. All the combined contributions shown on this slide demonstrate for the first time the use of catalytic rather than stoichiometric quantities of transition metal to form the desired carbon-carbon bond. Secondly, they provide the first selective cross-coupling, and based on these reports, the 3 key ingredients for a successful cross-coupling were identified. Now we will have a look at several important cross-couplings and their initial reports. After the detailed work of Keresh, the scientific community became aware of the potential of cross-couplings and more people became involved, leading to further improvements. A major milestone was reported independently by both Koryu and Kumada and co-workers. Both introduced nickel as a transition metal in the cross-coupling of organomagnesium partners. The idea to introduce nickel was based on previous work by Yamamoto, who had successfully isolated the first nickel-aryl halide oxidate addition complex, and Semmelheck's related work on the nickel-catalyzed homodimerization. Apart from the selective cross-coupling, also the introduction of a phosphine ligand by Kumada are noteworthy breakthroughs in the field. The Koryu-Kumada coupling was for example applied in the synthesis of an early biaryl intermediate of the HIV protease inhibitor atazanavir. Despite its novel approach to construct carbon-carbon bonds, the high reactivity of the organomagnesium compound is the major limitation of this methodology, since they react with a variety of electrophiles and are also sensitive to water. The Kumada coupling can also be catalyzed by palladium instead of copper. The palladium-catalyzed variant was first reported by the group of Murahashi. Tetrakis triphenylphosphine palladium, or also often referred to as tetrakis, is used as both palladium source and ligand. The idea of using palladium in the Kumada coupling can be attributed to earlier work by Heck. The introduction of palladium in the field of cross-coupling can be traced back to a series of publications in 1968 with Heck as sole author. In these, Heck describes the coupling of organomercury reagents with various alkenes catalyzed by palladium. One of his earliest examples is shown on the slide. Most likely, Heck was inspired to use palladium based on its prior use in the Wacker oxidation. Improvements were made in the following years by both Heck and Mizrachi, for example, as shown by replacing the toxic organomercury reagents by organohalides inspired by earlier work of Phyton on the oxidative addition products of palladium and organohalides. The Mizrachi-Heck reaction has become a popular method in the arsenal of synthetic chemists due to its broad functional group tolerance, but of course it requires an alkene. A large-scale application of this methodology was reported by Flahiv and co-workers at Pfizer in the final step of axitinib developed for the treatment of cancer. Another very nice example of a cascade double Heck asymmetric cyclization was demonstrated by Key and co-workers as a crucial step in the total synthesis of xestoquinone. From this point on, palladium would be a transition metal to consider for future applications apart from copper and nickel, who had dominated the landscape thus far. Over the years, the scope of palladium in cross-couplings, as you will see in the next slides, would grow, and often palladium would outperform other transition metals. For example, in the field of acetylene couplings, copper salts were the catalyst of choice early on. However, this changed as in 1975, 3 groups, Kassar, Heck, and Sonegashira, independently described the first palladium-catalyzed coupling of acetylenes with aryl and phenyl halides. We observe that the combination of copper with palladium by Sonegashira allows much milder conditions versus the conditions with only palladium of Kassar and Heck. Most likely, the base and copper result in the formation of a copper acetylide which accelerates the transmetallation step. The combination of palladium and copper developed by Suzuki-Miyaura is still used in modern applications. For example, in the 20-step total synthesis shown on the slide, a late-stage Suzuki-Miyaura coupling is used. The mild conditions leading to a high functional group tolerance, combined with the availability of acetylenes and aryl halides, places the Suzuki-Miyaura method in an excellent position for both early and late-stage modifications. Of course, the need of acetylenes also limits the product diversity. An important milestone in the field of cross-couplings was reported in the 1970s by Negishi. Less reactive organic metallic reagents, such as organoaluminium and organozinc reagents, were introduced by Negishi. Also, Jutan reported the use of organozinc reagents in cross-coupling around the same time. Further studies on the coupling itself, mostly by Negishi but also by other groups, and studies to generate zinc species by, for example, the Knochel and Uchiyama group, have resulted in a broad scope and thus made this an essential reaction for the synthetic chemist, especially in the field of total synthesis. An example of the Negishi reaction in industry was reported by chemists at Abbott. The zinc species was made by lithiation, followed by the slow addition of the zinc source. Next, the aryl bromide and palladium ligand were added to obtain the desired intermediate on large scale. Also note the ester functionality on the intermediate, which would not be compatible with an organomagnesium reagent. The major downside is the operational complexity and waste of the zinc species, which explain its overall limited use in industry. Most importantly, having demonstrated the reactivity of alternative organometallic derivatives instead of organomagnesium species, Negishi set the stage for the uncovering of milder, less electropositive metal coupling species. Other alternative organometallic derivatives followed shortly after the pioneering work of Negishi. Two key contributions from Stille and Migita on the selective coupling of organostennanes are shown, but pioneering work by Eborn, Atwell, Bokerman, and Matsumoto paved the way. Also, the expansion from alkyltene to iotine reagents by the group of Beletskaya is an important contribution to the field. Stille and his students further optimized the cross-coupling of stennanes with organohalides. The Stille coupling can be used in the synthesis of complex compounds. For example, in the synthesis of methyltrinol, the late-stage tandem Stille microcyclic coupling is followed by oxidation and deprotection to produce the desired natural product. The introduction of organolithium species can be traced back to a report of Murahashi and co-workers. The Murahashi coupling is less known due to the strong reactivity and difficult handling of organolithium reagents. Recent development, shown by the example of the Verheyen group, have improved reaction conditions by using modern catalytic systems and appropriate conditions. The major advantage is the low cost and availability of the lithium reagents, but the functional group tolerance remains a challenge even today. Another alternative organometallic discovered later are silanes, which can be linked to the work of Hiyama and co-workers. The first report, in 1988, by Hiyama shows that the inclusion of a fluorine source, thus in this case, in the reaction mixture can be used to activate the organosilane towards transmetallation. This methodology was expanded by the group of Denmark. For example, by using other silane reagents, a Bronsted base instead of a fluorine source could be used for the activation. The most known and used organometallic coupling partner and related cross-coupling are boronic species used in the Suzuki-Miyaura cross-coupling. The first catalytic cross-coupling of boronic species can be linked to a report by Miyaura and Suzuki in 1979 based on earlier, similar but non-catalytic coupling data of both Negishi and Hegg. The facile adaptation by both academia and industry of this carbon-carbon bond forming strategy can be understood by the boron coupling partner, which, contrary to previous couplings, offers easy handling, air and moisture stability, is less toxic, and has more easily removed less toxic byproducts. It's also important to note that the base plays multiple roles, such as the activation of the boronic species, and thus is required for the reaction. The number of examples of Suzuki-Miyaura couplings in the pharmaceutical industry are vast. An analysis published in 2016 of past and present synthetic methodologies applied in medicinal chemistry shows that three couplings are used frequently. These are Suzuki-Miyaura, discussed before, Buchwald-Hertwig coupling, to be discussed, but most heavily used of the three is the Suzuki-Miyaura coupling. In fact, Suzuki-Miyaura cross-coupling is in the top 5 most frequently occurring reactions. Examples of biphenyls prepared via this coupling in approved drugs are often observed, as you can see by the examples. A second early example in the total synthesis of polytoxin was reported by Kishi and highlights the importance of base. Use of thallium hydroxide gives complete reaction upon mixing of the reagents, while potassium hydroxide requires 2 hours to reach high and yet incomplete conversion. To complete the carbon-carbon palladium-catalyzed cross-couplings, we must also mention 2 more related couplings developed in the late 1990s. Both lead to ketone products and both make use of a thioester as a coupling partner. First, the Fukuyama coupling is a palladium-catalyzed cross-coupling with an organozinc halide and a thioester. The reactivity and the mechanism are like the Negishi coupling, but a thioester is used instead of an organohalide as cross-coupling partner. Again, due to the use of the zinc reagent, the coupling can be done under mild conditions, thus has a broad functional group compatibility, but also results in operational complexity and large amounts of zinc waste. A final noteworthy addition to the carbon-carbon cross-coupling toolbox is the Libeskind-Schur coupling. In the original report, a carbon-carbon bond is formed from a thioester and a boronic acid using palladium as catalyst and stoichiometric amounts of copper. The critical transmetallation step is proposed to go via a copper and palladium bimetallic complex with all the coupling partners present. Apart from thioesters, also thioethers, thioamides, thioalkynes, and thioisocyanides have been used as electrophiles. Also, the nucleophilic boronic acid partner can be changed to, for example, stananes, indanes, and others. Variants catalytic in both palladium and copper have also been developed after the initial report. A challenge which remained unaddressed is the cross-coupling of non-carbon nucleophiles to form carbon-heteroatom bonds. An important contribution was made by Miyaura and co-workers developing carbon-boron bond formation chemistry. The introduction of boron reagents with the boron-boron bonds, a preformed phosphine palladium catalyst, and the use of a mild base were described in 1995 by Miyaura. Even today, bisphenylglycol diboron, bis-diphenylphosphinoferrocene dichloropalladium, and potassium acetate are a smart choice for your first borylation in the lab. The use of a mild base instead of a strong base is very important since it prevents further Suzuki coupling of the aryl boronate ester product. The Miyaura borylation is an attractive route to synthesize borylated compounds under mild conditions starting from readily available materials. Borylation and Suzuki-Miyaura cross-coupling have been combined in a one-pot two-step procedure, for example early on by Giroux and more recently by the Molander group. After completion of the Miyaura borylation, the Suzuki coupling is feasible simply by the addition of a second aryl halide and a strong base without in situ isolation of the boronate. Cross-coupling towards carbon-heteroatom bonds with well-known nucleophiles such as thiols, amines, and alcohols was early on studied by Migita. For example, already in 1978 he described the formation of a carbon-sulfur bond with catalytic amounts of palladium. Further studies were conducted by a group of Migita, Mahashi, and Beletskaya, and others. Another important contribution, also from the group of Migita and co-workers, was reported in 1983, where he described the first carbon-nitrogen palladium-catalyzed bond formation. In 1995, both Buchwald and Hertwig improved the pioneering work of Migita by replacing the amidotin reagent by an amine and a strong base. The protocols developed by Buchwald and Hertwig were compatible with a broad variety of secondary amines and avoided the water-sensitive and toxic tin reagent used by Migita. Both protocols were quickly adapted by the scientific community. Buchwald, Hertwig, and other groups further improved amination and improved or expanded the coupling to other nucleophiles. For example, Buchwald and co-workers also reported the mild palladium-catalyzed carbon-oxygen formation of diaryl ethers in 2006. The Chan-Lam-Evans coupling should also be mentioned since it's complementary to the Buchwald-Hertwig coupling. The cross-coupling reaction partners are an aryl boronic acid and a nucleophile such as alcohols or amines, and relies on stoichiometric copper to form the desired carbon-heteroatom bond. Thus, it also follows a different mechanism compared to the palladium-catalyzed Buchwald-Hertwig coupling. At this point, we have only focused on the narrative of the development of conceptually new reactivity cross-couplings. Of course, the deep understanding and continuous fine-tuning with the aim of increasing functional group compatibility, thus increasing applicability, was and is still ongoing at this point. The importance of these modifications and manipulations should not be underestimated, since they made it possible to begin employing carbon-carbon coupling chemistry in the synthesis of biological important molecules, even on large scale. The detailed work by both Buchwald and Hertwig on the mechanism and the development of improved catalytic systems for the amination is an excellent example to illustrate the potential impact of fine-tuning in cross-coupling. Thanks to these developments, the Buchwald-Hertwig amination has become a fundamental tool in organic synthesis for the formation of carbon-nitrogen bonds. The initial report previously discussed relied on the orthotolyl phosphine ligand. This allowed the amination of aliphatic and cyclic secondary amine nucleophiles with aryl bromides or iodides. Less reactive electrophiles and primary amines were not feasible. Both groups introduced a second wave of ligands based on aromatic biphosphine ligands. The rationale was to improve performance by having the bidentate coordination of phosphine to the metal center, thus favoring reductive elimination over the competing beta-hydride elimination. Both groups independently reported BINAP and DPPF as ligand. The yield was improved and both the electrophilic and nucleophilic partner scope was expanded. For example, aryl triflates or alkyl bromides or primary amines were successfully cross-coupled. Further building on this rationale, even more steroid bulk was introduced, resulting in, for example, DTBPF and pop-type ligands such as xanthos. With these ligands, the scope was again expanded to include, for example, aryl chlorides and also weaker nucleophiles such as anilines and amides for the first time. In a third wave, both switched to sterically hindered monophosphine ligands. The rationale was to increase electron density around the metal center, thus accelerating the slow oxidative addition step, and secondly, keeping the reductive elimination fast by having the steric hindrance present. In the lab of Buchwald, a series of biaryl phosphines such as DPHOS and XPHOS were developed, while Hertwig investigated 3-alkylphosphine and Josephos type ligands. Both series improved catalytic efficiency, allowed the reaction under milder conditions, and expanded coupling partner scope to, for example, aryl chlorides and various pseudohalides, coupling with heteroaryl halides, and selective amination with ammonia. In the previous slide and throughout this presentation, pseudohalides were already shown or mentioned. Historically, the initial focus in cross-coupling was on finding new nucleophilic partners, so the organohalide, mostly iodide or bromide, remained the same for many years. The first pseudohalide reported in cross-coupling was geranyl acetate by Negishi in 1982. The major advantage is the easy access to the alcohol precursor compared to the corresponding halogen precursor. The most commonly used pseudohalides in cross-coupling are derived from alcohols and are the sulfonates such as triflate and mesylate. Apart from carbon-oxygen, also carbon-carbon, carbon-nitrogen, carbon-sulfur, and carbon-phosphor bond pseudohalides have been reported. Some examples are shown here, but this list is by no means complete. An impressive example of how you can exploit this was shown by Schoenenberg in 2018, where they describe a method for a triple selective sequential carbon-carbon coupling employing a single catalyst. However, it should be said that the selectivity is not general and depends on substrate, catalyst, and reaction conditions. Of course, the ultimate goal would be to selectively achieve CH functionalization, and if possible, in complex molecules. This would be the most efficient strategy, but this field is not discussed today. The most popular of cross-couplings in organic synthesis has always been and remains the Suzuki-Miyaura coupling. Since boronic species are essential in this coupling, alternative boron species have been investigated thoroughly. Initially, alkynyl boranes and catechol boronic esters were used. However, by now a wide variety of boronic species are available. Some of the most popular ones are shown, yet more are out there. Reasons for the development of new boronic species are easy preparation, increased stability, easy to handle solid boron analogues, development of efficient synthetic strategies, boron species stable towards silica and aqueous workup, and finally increased reactivity in the transmetallation. More details about the pros and cons of each can be found in the references below. trifluoroborate salts and metaboronates are the most developed systems. For example, as reported by Molander and co-workers, stable trifluoroborate salts were prepared and subsequently derivatized by cross-coupling with various aryl chlorides. Secondly, iterative cross-coupling strategy using metaboronates has proven to be highly efficient in organic synthesis, for example in the synthesis of polynatural products such as retinal. The synthetic approach is only feasible because meta is stable under certain Suzuki-Miyaura conditions, but can be deprotected rapidly to unmask another boronic acid reactive group. Carbon-relative variations of almost all well-known cross-couplings have been reported by different groups. CO insertion is a fast process, so it can be easily incorporated in the catalytic cycle. Carbon-relative reactions are an efficient methodology for the synthesis of carbonyl-containing compounds. Mostly ketones are formed, but also, for example, amides, esters, and alkenones are feasible. Of course, one should be careful when working with a toxic gas as carbon monoxide. Despite this, solid CO precursor compounds and commercially available simple lab equipment are out there, thus omitting the necessity of specialized pressure equipment and CO gas bottles. Some of the examples presented today have received more attention than others. Nonetheless, all the transformation and following mechanistic and optimization research have played an important role in the development of cross-coupling. This effort has pushed the boundaries of possibilities and led to the current state of the field. The field continues to receive attention from both the academic and industrial community. I personally also look forward to the next developments in the field of cross-coupling. So what's next? Cross-coupling is still evolving by, for example, looking into the merger of cross-coupling with other fields such as photoredox, electrochemistry, high-throughput screening, and artificial intelligence. By looking at new types of related reactions such as cross-electrophile coupling, by looking at novel, easy, accessible pseudohalides, by looking at the latest analytical techniques to further understand the mechanistic aspects, or by generating and theoretically mapping new and known catalytic systems, and of course also CH activation remains an area of interest. I would like to close today's episode by mentioning that only the highlights were touched, however many other relevant contributions were made. For those who want to learn more, on this slide you can find some excellent literature references which were used to construct this episode. I might have also mispronounced some of the names, for which I apologize. Finally, thank you for your attention and feel free to reach out to either me or Matt in case of any questions. If you're interested in more episodes in the future to cover some of the recent trends, for example, you can also let us know.
Thank you, Thomas, for an excellent lecture on cross-couplings, covering many historical and also practical aspects of this field. And I would just echo Thomas's encouragement to dig deeper into the relevant literature on your own. We'll continue this module in our next lecture as well. See you all next time.